Welcome everybody. Welcome to Nonlinear Optics. Today we want to talk about another, well, perhaps the most important consequence of the nonlinear Schrödinger equation that we discussed last times. Remember, we were discussing the nonlinear index of refraction. We first discovered that there are things like filamentation, or first of all, of course, self-focusing, then filamentation, where actually divergence or diffraction was counterbalanced by self-focusing. Then we went to the time domain, and we were discussing the propagation of pulses, of short pulses, and the idea there is that we change the refractive index in time as the pulse evolves. And this leads, of course, to a time-dependent phase, and as a consequence, to new colors. And, well, new colors, that's always the thing we are most interested in nonlinear optics. The pulse propagation we found, and actually this is subject to a course on short pulses in the realm of linear optics. So the pulse propagation of short pulses in matter is described by, or can be described by a Schrödinger equation, by a regular Schrödinger equation. And then as a consequence for the nonlinear case, we have the so-called nonlinear Schrödinger equation, which, I emphasize this once more, has nothing at all to do with quantum mechanics. What we discussed last time was what I just mentioned, namely the creation of new colors. And we did this in a regime where dispersion, so where the effect, so where pulse dispersion, where the effect that is dominant, or that's the only effect in linear optics, so where pulse dispersion, pulse broadening, and so on, chirp is another important noun in this context. So we discussed self-phase modulation without pulse dispersion, and now we want to put both together, and this leads to solitons. So solitons is a very interesting phenomenon, and not only a phenomenon in nonlinear optics, rather it was discovered, well, in 1834 by John Scott Russell. And this is an interesting story, and I would like to tell you this story. So here are a few slides on that. Yeah, so I just mentioned they were discovered by John Scott Russell. Here you see a portrait of John Scott Russell. And, well, it's a celebrated thing, and therefore there's actually a plaque noting this, well, kind of event, because the discovery of solitary waves was made in a rather spectacular way. So what you see here is where this plaque here is mounted. Under a bridge, or at a bridge, and there's a channel here, and well, here's a bigger view of that. Yeah, so a channel, and these channels in the 18th, 19th century, they were used, well, not for holiday and leisure things as today, but they were used to transport mass goods, like coal in particular. Also from the coal mines to the factories. And, well, these boats, they were actually drawn by horses that were pulling these boats through the channel. Well, here you see another one. Actually, this one is a channel that crosses probably another river or something like that. Yeah, so it's a bridge of a channel. So you see there were really water streets with crossings and these things. Okay, and here's a drawing of John Scott Russell, drawing made by John Scott Russell. So here you see the boat, and here you see the horse is pulling this boat, probably a very heavy one, 6 horses or so, right? Another discovery. So he apparently was kind of responsible for these channels as an engineer or something, and he wrote, after discovering this phenomenon we are talking about, I was observing the motion of a boat which was rapidly drawn along a narrow channel by a pair of horses. Well, not 6, but a pair of horses. Then the boat suddenly stopped. Not so the mass of water in the channel which it had put in motion, which the boat had put in motion. It accumulated round the prow of the vessel in a state of violent agitation, then suddenly leaving it behind, rolled forward with great velocity, assuming the form of a large, solitary elevation, a rounded, smooth, and well-defined heap of water, which continued its course along the channel, apparently without change of form or diminution of speed. And now the nice thing, I followed it on horseback and overtook it still rolling at a rate of some 8 or 9 miles an hour. 8 or 9 miles an hour, that's pretty fast. So the horse had to gallop, I would say, preserving its original figure without some 30 feet long, so 30 feet, 10 meter long or so, and a foot to a foot and a half in height. So half a meter in height. Its height gradually diminished, and after a chase of 1 or 2 miles, I lost it in the windings of the channel. Such, in the month of August 1834, was my first chance interview with that singular and beautiful phenomenon, which I have called the wave of translation. So today we call it solitary waves. Well, this observation was a controversial one because it didn't fit to the physics at that time, to the physical understanding at that time. So it was at odds with the theory of waves by Newton and Bernoulli. And well, if you believe that physicists are always open-minded and critical to existing theories and so on, well, this is just one counterexample. Yeah, so physicists also, and I hope you don't do that, so you remain critical throughout your career. Yeah, so physicists are also preoccupied with their prior knowledge, biases, and so on and so forth. And what's even worse, physicists also believe in authorities. Newton, for example. And so John Scott Russell had actually a hard time to convince colleagues that his discovery was not made up, that this was a real observation. Well, today it would be a little bit easier for him. Yeah, so he just could put his GoPro camera on top of his head and then ride with the horse. That would have been nice, but at that time this was not possible. But on the other hand, nowadays chances to observe such a thing for the first time are probably less likely than at that time. Okay, yeah, and then there was a reenactment of this thing here. So you see this similar channel. So they tried to reproduce it. And one of my colleagues, Ulf Peschel, he, as a young man, was standing here somewhere. I don't know. So he probably changed too much. So you may ask him who he was or who he is. So this was, I guess, 150 years later or so, or even more. Okay, well, it took actually 60 years for physicists to understand it. And yeah, so the achievement was made by Koldewig and de Vries. So he was the PhD student of Koldewig. Yeah, so you see that he got very old, more than 90 years, and his PhD student died 10 years or almost 10 years before him. Anyways, so this was Koldewig and de Vries who solved this problem. Yeah, so the de Vries, so he was a professor of mathematics, and he became a high school teacher and made his career as a teacher. Yeah, and well, here an animation, but that's perhaps not so important. So where are these solitary waves discovered by John Scott Russell? Where can they be found? Of course, not only in channels, but they are also found in oceans. So here you see actually a sequence of solitary waves. So probably the photo was not made because of the solitary waves, but because of this, well, fleet of early aircrafts, probably around the First World War or so. Yeah, so here you see another pattern of solitary waves. And what you see here in particular is that there are solitary waves in two directions, and this gives us a first, or yeah, provides a first basic property of these solitary waves. So what you see is, well, we have two solitary waves or several solitary waves in different directions, here approximately at 90 degrees or so, and they cross each other without disturbing each other, without destroying each other. So this is one of the characteristica, one of the trademarks of solitary waves. And here you see the Koldewig-de Vries equation. Yeah, so you see, of course, a nonlinear differential equation, a nonlinear partial differential equation. So these solitary waves, so the Koldewig-de Vries equation also describes the tsunamis, yeah, so which travel in 4,000 or more than 4,000 deep waters, and their widths can reach not these 10 meters as described as the solitary wave discovered by Russell, but their widths can reach 100 kilometers or so, right? Well, there's another historically very important kind of solitary wave, or actually an incarnation of the Koldewig-de Vries equation, and this is the so-called Fermi-Pastor-Ulam-Zingon experiment. So usually in the literature you find it by the name Fermi-Pastor-Ulam experiment. And let me tell the story about that. Yeah, so here you see the FP and U. So this is Fami, this is Pastor, and this is Ulam. I think I don't need to say much about Fami. The other two men, they are less well known. So this Ulam was a Polish scientist of Jewish origin, and he made it out of Poland just 10 days or so before the German invasion, and he succeeded to rescue his family, in particular also his sons, and his brother, while his father and other members of the family died in the Holocaust. He joined the Manhattan Project in the US and worked together with Fami, of course, but also with Teller, and he is one of the fathers. Yeah, so Teller is considered the father of the thermonuclear bomb, but actually the first design by Teller was wrong. and Ulam, together with Fami, proved that Teller was wrong. And he then devised, together with Teller, the scheme of thermonuclear, so the hydrogen bomb, of thermonuclear bombs that is used, well, to the present day, not only by the Americans, but also by the Russians, at that time, Soviet Union, and it was Andrei Sakharov who made the same invention, apparently. And you may know Sakharov later became a dissident, in opposition to the Soviet regime, and later received the Peace Nobel Prize. So John Pasta is another very interesting person, the youngest of these three men. He was kind of the first, software engineer, one could say, right? Computers were not really invented when he started to study physics, so he didn't really have the money to study physics. So he started anyway before the Second World War, then was drafted to work for the US Army on radar and cryptography and so on. And after the war, through a certain bill that was passed by the Congress, he was able to continue his studies and studied physics. And he was the one who designed the software and so on. But he was not the only one. Yeah? And now we come to the T, to Mary Tsingu. I should actually check whether she is still alive. I think so. And she was one of the notable programmers of these early machines. And the point at that time was, it was around the Korean War, and so many young men were drafted, had to go to the army. And so when institutes running these computers were looking for programmers, they at some point started to prefer women because they were not drafted and would continue or could continuously work on these, well, very challenging things, very challenging tasks. And Mary Tsingu was one of these, particularly particularly a good programmer, apparently. And one other anecdote there was that they were bluntly told, so these ladies, young ladies, were bluntly told that they would earn less than men working on the same thing with the same qualifications, because men have to feed a family and women, well, I'm not sure what the logic was. The logic also continues on that paper that was written for this famous experiment, because Miss Mary Tsingu was not on the author list. Only Fami, Pasta, and Ulam, and actually Fami was already dead when the paper was finally published. And Fami even dismissed this, this paper as minor. So they didn't publish it in a prestigious journal. But Fami was wrong, because this experiment was remarkable for several things. Namely, first of all, it was the first example of a computer experiment, of a computer simulation. And then I have to tell you what they actually simulated. What they simulated was kind of a string where the coupling is nonlinear, right? And what Fami expected was that Yeah, so if other modes are excited, that finally the energy in these higher modes, in these faster oscillations or shorter wavelengths, they will eventually dissipate, and only the fundamental mode would remain. Right? So they programmed it and probably ran the program longer than anticipated. So on one of these early computers with, I think, 2,600 or so triodes, so electron tubes, and a number of diodes and so on and so forth. Yeah, so complicated machines, and also machines prone to defects. So this is how they looked. This machine looked like the Maniac 1, and here you see ladies working as operators of these machines. Here's her program. So new nonlinear vibrations, and the method, the numerical message, the shot method. Right? Very interesting. Well, what happened was not what Fami expected. Namely, these vibrations here, so these excitations of the higher modes, well, surely they were excited, but eventually all the energy would go back to the fundamental mode, and all these higher modes would vanish at a certain point, and of course then the game would start again. Okay, well, this is not the only example. Rather, the Einstein equations of general relativity are inherently nonlinear. And now, if in the case of stationary situations, time-independent situations with rotational symmetry, they can be described by the so-called Ernst equations. And the solutions of this equation also supports solitons. And I may mention that some of our faculty or former faculty, so Meinl is still around here. Neugebauer was a professor here, a very prominent name. And also Strudel, I think, of course, he's no longer here, but he still is alive. Yeah, so Strudel is also important for other things. Yeah, so if you know something about the PHYSIKALISCH 1956, he is an important name on that. Okay, well, there's another nonlinear partial differential equations with solitons as a class of solutions, and this is the Sine-Gordon equation. And the name is actually funny because it's just a bun on the Klein-Gordon equation. Yeah, so if you replace the term m squared phi in the Klein-Gordon equation by a sine, therefore the name Sine-Gordon equation, right, so it's just a joke, then you arrive at this equation, and it plays a role in plasma physics and superconduction, Josephson contacts, and so on and so forth. And it can be kind of, it can be visualized in with this kind of mechanical analogon, where you have a string of pendulums that are coupled by springs, as shown here. And then if you would throw over a number of these pendulums, so quickly throw them to the other side, then a wave is excited that keeps its shape. Well, it's a soliton. Yeah, so looks like that. And again, also these solitons, they can cross each other and then continue as if nothing would have happened. Well, here's another picture, nice picture that I found somewhere. Okay, now to optics. In optics, things are more complicated, and therefore it took, well, basically 150 years before optical solitons were discovered. Yeah, so we know, of course, now the nonlinear Schrödinger equation here in standard notation, and this is a form that we derived last time, right? And then you could identify, yeah, so just as a repetition here, right? This nonlinear Schrödinger equation is not only used in optics, but also in quantum mechanics. So if you want to describe a system, a Bose-Einstein condensate, then it can be described by the Cross-Pitayevsky equation, which is similar to the nonlinear Schrödinger equation. Okay, but now to the optics. In 1973, right, so 140 years later, 140 years after Scott Russell, these two physicists at the Bell Labs predicted solitons in optical fibers, and then it took another, well, 7, 8 years until they were, well, experimentally proven by Mollenhauer, Stolen, and Gordon. And why did it take so long? Well, one reason was, of course, that one needs a laser, and the laser was still fairly young at that time. Perhaps not too young. One needs optical fibers, and optical fibers, they were just being developed at around that time, right? So that you can produce an optical fiber that has a high transmission, a low absorption. That, yeah, so optical fibers, they were known long before, but optical fibers of high quality, this was only developed at that time by a physicist of the name Kao, who, I think it was already in this century that he received the Nobel Prize for optical fibers. So also a fairly young thing. Yeah, here you see these persons who did this first, and here the paper in Physical Review Letters in 1980. Right, a short pulse laser. In this case, it was a color sender laser beam, so which is hardly known at today. So they used 7 picosecond pulses and a 700-meter long single mode fiberglass, silica glass fiber. So and what we need is, and we discussed it already last time, what we need is negative dispersion. And of course, if you are in the optical regime, in the visible regime, the dispersion of material is positive. And we also learned that self-phase modulation is positive. But what we need is that both counter interact, so that they compensate each other. Dispersion, so linear pulse dispersion on the one hand side, and self-phase modulation, from which we know that self-phase modulation produces a positive chirp. This was one of the results of last lecture, right? And therefore, we need, for the linear optics part, for pulse dispersion, we need negative dispersion. And usually you don't get that in the optical regime. But you can have it if you go to wavelengths in the near infrared, so 155 micrometers, still a very important wavelength today. It's called the telecom wavelengths. Yeah. And there one can produce, so there certain glasses have negative group velocity dispersion, so a negative K double prime. Yeah, so the derivative of the wave number k, the second derivative of the wave number k with respect to omega. This should be negative in order to have a chance to produce solitons. And here you see this. So short pulses, and the higher the power, very interestingly, the narrower the pulse. Let's hope we can understand that. And if you go too high, then actually several pulses show up. Actually, this is just a pulse pair. It looks like 3 pulses, but this is an autocorrelation, and if you take an autocorrelation of pulses, then it looks like this. So these are actually double pulses. Good. Yeah. So all the equations that I mentioned so far, they can be solved by a mathematical method that's known as inverse scattering theory, which, however, would take more time than available in this lecture. So this can be done. Yeah. So it's a numeric. So you can base numeric procedures on inverse scattering theory, but also analytical approaches. We won't do that, but you see that this is also fairly recent. Only, well, not even 50 years old. Let's start with an elementary approach before we really look at the nonlinear Schrödinger equation and try to solve it in a traditional way. So an elementary approach. And for this, an illustration. So think about, well, a group of people who want to travel some distance, and one person has a big car, the other one a race car, and this poor guy only a bicycle. Nevertheless, they want to stay together, and now they are lucky because they have a road made out of rubber, such that the heavy car depresses the road, so that it has a dent. And then if you let run the race car in front of this heavy car, it always has to go hill up, while the bicycle, if arranged in the right way, always goes down the road, right? And in this sense, you see that these 3 very different vehicles can stay together. Yeah, so just as an illustration. And actually, this illustration goes this. So if you think about a fast car as the blue wing of a pulse, and the slow vehicle, the bicycle, as the red wing, then you see actually that this is a chirp, what we have here. Okay, anyway, let's try to get a little bit quantitative. So the necessary condition for the creation of a soliton, as already indicated, is that you compensate the chirp, which we describe by the chirp parameter B, that you compensate the chirp that is produced by self-phase modulation and the chirp that is produced by pulse dispersion, right? And this is indicated here. So B due to self-phase modulation, and here B due to second-order dispersion. Second-order dispersion because we have the second derivative of k, of the wave number k, with respect to the frequency omega. Now, we just look up the formulas from the previous chapter, and we find that this chirp parameter, that this is given by this expression here, right, where you see basically the nonlinear index of refraction and the intensity. And of course, for second order dispersion, we have this expression where you see here the pulse duration, the inverse pulse duration. The larger A0, the shorter the pulse duration. So you see that this chirp parameter gets the larger, the shorter the pulse duration, as you would expect. Okay, now we want to equate both, and this is shown here. Many quantities here cancel. And then we find that if we divide the intensity through the pulse duration, more strictly speaking, multiply it with the pulse duration, or the square root of it, then it has to obey this condition here. You can also reformulate it, and instead of intensity, use the electric field squared. And if you take the square root, then you find here an expression. Yeah, so tau is now the pulse duration. Yeah, so tau, so we have here tau squared is 1 over A0. So you find that this is the area under the pulse. Yeah, so pulse with times its amplitude, that this should obey this condition here, where we have second order dispersion and the nonlinear index of refraction. And all the other numbers are not so important. Yeah, so Z0, this would be 300, the vacuum impedance, 377 ohms. Yeah, but yeah, so these are just natural constants. The other things, these two here are important. Yeah, second order dispersion and the nonlinear index of refraction. And you would expect both, of course, in this equation, necessarily. So another equation or another condition, yeah, so you can also write it in this, so you can also, if you want to compensate nonlinear self-phase modulation and pulse dispersion, then you can also put it in this simple form, that the dispersion length has to be equal to the nonlinear length. Okay, now we want to look at properties of the nonlinear Schrödinger equation, and you will see that we'll discover a slight problem that I want to discuss here. So we compare the nonlinear Schrödinger equation with the regular Schrödinger equation. Well, actually, it's already a nonlinear equation, Gross-Pitayevsky equation. Well, what you discover is that this equation here is analogous to this equation here. However, only if p is larger than 0. Right? Now let's see what p is and whether it's larger than 0. Right? So what we find is that p is the sine of k double prime divided by 2 times the dispersion length. And this is kind of unfortunate, because we said that because we don't have materials where n2 is negative, we need k double prime to be negative. Yeah, so nature is not kind enough to us to provide examples or nonlinear indices of refraction that are negative. They're all positive. And so we have to use a negative dispersion, negative second order dispersion, negative group velocity dispersion. Well, and then p, unfortunately, is negative. But we said that this is only a nonlinear Schrödinger equation in a strict sense if p is positive. So what to do? Well, here's the solution. If p is negative, and it is negative, then we would multiply our equation 3, our nonlinear Schrödinger equation, by -1. Then we have the right side sign for p. but at the expense of the wrong side on the left-hand side. What can we do? Well, we can take the complex conjugate of this equation and solve this equation for the complex conjugate. And if we have the solution for the complex conjugate, then obviously we also have the solution for the complex conjugate of the complex conjugate. Yeah? So for psi. Well, so you see, it's not a real problem. So what we can assume without loss of generality is that P is larger than 0. Also, we kind of know that it's not. Right? Okay, well, the potential term here is minus q times the magnitude squared of the wave function of psi. So it depends on psi, and this makes this a partial differential equation, nonlinear. And now if q is larger than 0, then psi digs its own, not grave, but its own potential. Yeah? And then the solution, if this is the case, quite obviously, if we don't have an attractive potential, then we wouldn't expect localized solutions. So therefore, we need q larger than 0. Yeah? So P is larger than 0, and q is larger than 0. Without loss of generality. Yeah? So even if the contrary is true, if we solve instead for psi star, for the complex conjugate, we can say that P and Q, that both are positive. Good. So, this was too fast, I'm afraid. We want to solve this partial differential equation. And the best way to solve a differential equation is to know the solution. And I think I made this kind of cheap joke several times, yeah, to solve an equation by knowing the solution. But I would like to emphasize one aspect here once more. Yeah? So when you first encounter this method of an Unsubs, yeah, which is a German name for an educated guess, when you first encounter this concept, then you might think or might feel, well, this is, so this is unfair to, at least to the beginner. Yeah? I have to have 20 years of experience in order to make the right Unsubs. Well, not quite so. As a physicist, at least. Yeah, so the mathematics students, they are not in as good a position as we as physicists are. As physicists, we know what we are looking for. We know that there are, we know how a solitary wave looks like. We expect a pulse, don't we? So, and a pulse has an envelope, and of course, there is the oscillation of the electric field below the envelope, right? And in this sense, we know how our solution should look like. And now we just need to write that down. And this is done here. Right? So what you see here is that we write this wave function as a product of the amplitude, which I call phi here, and the carrier wave, so the fast oscillation. So this here is the amplitude, say, of a femtosecond pulse, and then we have a frequency of several hundred terahertz or so below that. Right? Well, what I also should emphasize is that this pulse propagates, of course, in space and in time. And of course, also the wave here develops in this way. Right? So both depend on space and time. And both are real numbers. So if I decompose a complex function in this way, then I implicitly assume, and I would like to emphasize it here in particular, that both are real functions. So psi and theta are real functions. Good. So what do we do with an ansatz? We plug it into our differential equation, and to this end, I have to calculate all these derivatives. So the first derivative with respect to time, and the second derivative with respect to space. And I do this here. First derivative, which we don't really need, we just need it in order to calculate the second derivative. Okay, and then I find that I have here imaginary parts, which you find here in green, and here real parts. Actually, I multiplied with I, so, well, actually the green one are the real parts, and the red one are the imaginary parts. Yeah? So I multiply here with I, therefore I get here a minus sign, and so on and so forth. Yeah? Okay, well, and then I sort them according to real. So what I have basically are two equations that come out here. If I substitute this ansatz into it, one for the real part and one for the imaginary part, right? We made it simpler by producing two differential equations out of one. Yeah? So we have to solve two differential equations. Well, how do we do it? We make an ansatz. And how do we guess it? I mentioned it already in some sense. I said that the amplitude develops in space and time. So what we have is a disturbance that develops in space and in time. And the same thing is true for the phase. Yeah? And what is this? A disturbance that develops in space and time. This is a wave. Don't think about waves only as a sinusoidal thing, right? A wave is a phenomenon, is a disturbance that develops in space and time. Or in other words, a wave is something that obeys the wave equation, right? And what is the wave equation, or what? Well, of course, this is kind of a wave equation, right? But what is a wave or a solution of a wave equation? A solution of a wave equation is any function that behaves, that you can differentiate twice. So any function that you can differentiate twice, which has this argument here, is a wave. Yeah? So usually you have it in the form kx minus omega times t. So here it looks a little bit different. We divide it, or multiplied with wavelengths basically, right? Plus a few constants or so, right? So what you find here is the velocity of the wave. Well, and I put here an E on this velocity because we know already that this here is the envelope. This is the amplitude of this thing. Yeah, so this is the envelope of the pulse, and the other one is, of course, the phase. Okay, well, two new Ansätze. This is the plural of Ansatz in German. So you also learned a little bit of German today. Good. These are our Ansätze, our two Ansätze. So we calculate the derivatives that we need here in these differential equations that we want to solve. Yeah, so instead of solving the original Schrödinger equation, we solve these two differential equations. At least we try to do it. And, well, we need the derivative with respect to x. And you can find it. So what you have here is the chain rule, simply. Right? We take the derivative with respect to the entire argument, with respect to x minus velocity times t, and then the chain rule. And of course, you immediately find that this here gives 1. And I would take or use the abbreviation phi index y as this derivative. Right? And then I can do the same thing here with the temporal derivative. Good. Yeah, so we plug in this here into our differential equations. And we arrive at this thing here, yeah? At these two equations. Yeah, so we just simply plug it in, nothing more. Well, the next thing is, yeah, and there a little bit of mathematical experience is, of course, very helpful. So we multiply this with phi here. 29, we multiply with phi. Then you see that we have here phi and the derivative of phi. Right? You see this here. With here phi squared, well, and here also phi times the derivative of phi. Yeah? And if you integrate this, then you find that we have here that we have here the phi squared. You can check this just by taking the derivative of that, and you would arrive at this equation here. Well, yeah, this equation here. Good. Yeah. Well, now we have this equation here, and we need to do something about it. Now we need to think about what kind of solution we are looking for. And, well, we are looking for a solution that is a localized, that is a solitary wave, right? And so we have this integration constant c, and we want to determine what this integration constant c is. And in order to find the answer, we remember that we have a localized function. So a function that disappears, that goes to 0 as we go away from the maximum more and more. Right? As we make y, so this argument of this function, so this one here, this argument here, as we make this here larger and larger, it should, this function should decay. And the consequence is that c must be equal to 0 if we want to find a localized solution. Yeah? Of course, you can say, I don't want to make c 0. What happens then? Well, solve the equation. Yeah, that's your job. Solve it if you're interested in that. I'm interested here in solitary solutions. So I choose c equal to 0. Right? Okay, well, if c is equal to 0, then we can actually divide this equation 30 through the amplitude squared, yeah? Basically the intensity of the pulse. And of course, we assume that it's not equal to 0, but anyway, only mathematicians would have such thoughts, right? So for us, it is obvious without saying. Good. So this equation 30, which was the consequence of this equation here, and this was the consequence of, well, actually I don't remember. So this equation 30 has now a very compact form that we can integrate again, and if we integrate it, then we find this expression here, right? Just a constant. We integrate it. We get the argument, so which is this one here. Well, C prime can be set to 0. We just need to choose the time origin, the time 0 accordingly. Right? So, okay, good. Let's continue. So now we plug 31, so this equation that we got. Yeah, so actually, this is remarkable here. Right? So you see that we indeed have a function which has this characteristic argument for a wave. Right? So it's a very trivial wave here, right? With just a constant here. Yeah? But it is a wave. Yeah, so, and once again, yeah, so theta, never lose track of what we are doing. Theta is the phase. Yeah? We see how it develops here. In space and in time. Coupled, yeah, so the spatio-temporal development of this phase is coupled, as you would expect for a wave. Okay, now we plug in equation 31 in equation 28, so in the other equation, in this one here. Right? And this is done here, so we replace theta y by equation 31, and you find it here. In the second term, there's nothing to replace. The third term, we have the square of it, and you find it here, surely. And the last term is also doesn't contain a theta y. Well, this can be simplified and reordered a little bit. Right, so nothing in particular has happened, and now I multiply with p phi y. Right, and you see, same kind of trick. So we have here the second derivative of phi of the envelope with respect to y, and the first derivative. And if you integrate, then you get the derivative, or the so y squared. Just take the derivative and you find that we reproduce that. And also the rest here can be integrated, and we call it V effective, and you'll see why. Actually, here's the spoiler already. Same argument, we find that C double prime is equal to 0 because we want a localized solution, blah, blah, blah. And therefore, this equation here can be written in this way, right? And if you look at it, then it looks like energy conservation or so. Yeah, so a formula known from high school or so. Well, only the potential is a little bit more complicated than usual. It's not just a harmonic potential or a 1 over r potential or something like that. It has this peculiar form here, right? And now, physics comes in again. Now, let's use physics arguments. We said already that P and Q, that both are positive, right? P and Q are positive. And now we want to find a localized solution, a bound solution, which means that this potential V effective, so this kind of pseudo potential, that this has to be negative. Yes, this has to have a minimum somewhere, and therefore. So if this here is positive, then we have a fourth order potential that goes up like that. And if this also would be, if we wouldn't have, if this would be negative here, then we would add something to it. right? It would be a pretty boring potential, kind of potential. Right? So what we have to have is that this thing here is negative, so that the entire thing here remains negative, which means that this thing here should be positive. Which is interesting because what we have here are the wave velocities of the envelope and of the phase in a complicated or, well, not quite straightforward combination. So, one can show that this is indeed the case, that this is positive. And what you also get is that the velocity, the phase velocity, and the envelope velocity, that they must be different, right? And this is something interesting because it means that if the phase, so consider a peak of the electric field and the peak of the envelope, if they have a different phase, then the phase slips below the envelope, right? So as this wave propagates, the phase with respect to the envelope will constantly change, right? This must be like that when you're not in vacuum, because then the group and the phase velocity are different, and this is basically what we see here. So let's see, yeah. Okay, this is written here. Good. Yeah, so now we plot actually this potential for the interesting case, namely, for the relevant case, namely that P times Q is larger than 0, then we indeed have this structure here, right? Now you could think, or you could take this analogy kind of literally and think about the motion of a pseudoparticle, right? That evolves between this point named here 1 and 2, and then you would then you can write down an equation for the envelope, and you find this one here. Right. In any case, this equation 33, this can be integrated, and what you find as a solution is this one here with the secans hyperbolicus. Yeah, so you would have to take the derivative of this here and plug it in here in order to prove it. Yeah, so you can do this as a homework. And now if you would go and and write everything together, then you find, well, this here is the amplitude, and we found already the solution for the phase. Right? So this was our original ansatz. Remember, the original ansatz was phi of x and t times e to the I and phase. Right? So here we have phi. Yeah, so phi naught times the secans hyperbolicus. And here you have the complex exponential. And this here is theta. Yeah, ue times 2p, this here is theta. Yeah, and we find a value for the amplitude. Yeah, so you see that not every amplitude is here allowed, so that the amplitude assumes a particular form that depends on the nonlinear length, which is connected to p, and on the dispersion, no, the other way around, on the dispersion length, which is connected to p, and on the nonlinear length, which is connected to q. Yeah, so you would find the intensity hidden in this q. So this gives a certain amplitude phi naught. If you change the amplitude, if you change the intensity, then another amplitude would adjust, right? And you can reproduce of what we introduced in this elementary approach to solitons with this equation. Actually, I should have done it. Just comes to my mind. Okay. So we have a stationary profile for the envelope and the phase, but they develop in different ways. So I'm pretty much done for today. And my remote also thinks that I should stop here. But I need the final. No? Ah, the computer crashed. Yeah, then let's write down the final remarks here on the iPad. So we have here equation 40. And so we continue here. So this equation 40 that you just saw can be written as psi is equal to psi naught times the secant hyperbolicus of x minus velocity of the envelope. This is to do with the group. So this is the group velocity. Then we introduce here a length which is called LE here. So stands for the envelope. And then we have here the phase, the exponential of I kappa times x minus mu times tau. And then we would use for the length of this pulse 1 over the peak amplitude, and then 2p minus divided by q. Kappa is equal to the velocity of the envelope divided by 2p. Yeah, so you find this here. And then mu, which is a combination of both velocities. So we have the velocity of the envelope and of the phase divided by 2p. Yeah. And finally, some discussion here. Yeah, so the solution of the nonlinear Schrödinger equation is a wave packet that has a length that is inversely proportional to the peak amplitude. And this is just what we called in this elementary approach the area condition of solitons. Yeah, so this equation in the script, it's 41, and therefore it gets the same name here. So 41 says that the solution of the nonlinear Schrödinger equation is a wave packet, a pulse, that has the width LE, and LE is inversely proportional to the peak amplitude phi naught. So if the amplitude increases, the pulse length will decrease. And now remember what I have shown at the very beginning of this lecture, namely this article in Physical Review, letters from 1980, where just this thing was actually shown. Yeah, okay. Well, that's it for today. I would like to thank you for your attention, and we would reconvene next Monday.